Okay. So did you miss me? This is liking not having to come to class. Really? Maybe we should have more classes now to make up for it.
Or less.
All right. So you were working through the book and kind of talking about how instructions are represented in machine language, right? So, as we've kind of talked about historically, let's get some notes opened up here. Actually, give me 1 second. Can I get more than one of these at a time? I'll just do it later on. I'm going to put my 250 slides in my 355 slide set. So I forgot to switch slide sets. So I've switched slide sets for you. Okay, so a couple of things to look at here. So if we've talked about 3 kinds of programming languages, right? This is an old slide. So we had high level, low level, and machine language. And we've always said that high level languages had a one-to-many relationship with the CPU. Low level language, like our ARM or our LEG, V8, whatever, has a one-to-one relationship with the CPU. Now, ultimately, machine language is zeros and ones. So, at the end of the day, no matter how human we want to be, whether we want to be write software that's the most convenient for a human using high-level languages, or we want to write software that feels pretty geeky using low-level languages like ARM, at the end of the day, that all needs to be translated into something that the computer understands, right? And that's our machine language. Now, we've decided that machine language isn't made for humans. That is, we're not going to sit there and program using machine language. But the punchline is that we could. we could do it. We just would be probably extremely error prone. All right. So one of the things you looked at here is mapping. Oh, here, I'll just we'll introduce the slide and then we'll just reference the book. Mapping low-level instruction, so in our case, ARM or the LEG, whatever, to machine language. How do we represent an instruction in machine language? So now we go back to even another idea from kind of grander ideas of computer science, and that is data representation languages. So can you give me an example of a couple of, or at least one data representation language? JSON. So these some examples of these, like JSON. Anything else? XML. HTML is an example of a specific data representation language where JSON and XML are more generic. Like, hey, use these structures to represent whatever data you want, where HTML is an XML-y looking, because it's a chicken or the egg type thing. HTML came before XML, but XML is based on HTML. And now there's a thing called XHTML that is the HTML representation in correct XML when most web browsers don't support correct HTML. Yeah. All right. So in any case, we have these data representation languages, and these are not programming languages, right? Okay. What makes a language a programming language? If you're in 355, you can't answer. What makes a language a programming language as opposed to, in this case, a data representation language?
Logic.
Yeah, those 3 things.
What 3 things?
Yeah, like aspect, memory, and
and repetition. So asking questions, memory, repetition. So remembering stuff. So that's usually variables, asking questions, conditionals, things like that. And then repetition, loops and functions, that kind of stuff. Okay, so all programming languages, 100% of programming languages have facilities for those things. JSON, XML, HTML, they don't have facilities for those three things, right? Those are representation languages, whereas languages like Java and C# and C and C++ and Swift, these are all programming languages that have facilities for those three things. Is ARM a programming language? Based on all the stuff you've gone through in the book at this point, you now know it is, right? Because when the things you looked at while I was gone was you already knew how to store stuff, right? We can load things into memory, we can load things into variables, into registers, hardware variables, whatever. But now we can ask questions with our various branch instructions, right? Okay. And we can effectively implement loops using those same branch instructions, right? You just kind of branch back. you jump down, then you jump back if you're going to repeat that kind of stuff. And then also representing procedures. Did you do the representing procedures one, or is that where you stopped? That was the last one you did, right? Okay. So we've now seen how a low-level language like ARM, and I think the book references MIPS somewhat commonly, and then, Intel-based assembly, all these things, how they have all those telltale signs of our programming languages, right? All right, so at the end of the day, we need some way of getting our low-level programming language into our machine language, which is a data representation language, for our CPU to finally actually process it. Because machine language is not a programming language. Machine language as it's actually used is not a programming language. If we were to write machine language regularly as if it were a programming language, it does meet the requirements of a programming language because it has the facilities for those three things. It's just really difficult for us to operate with it that way. The reality is that when the CPU eats a line of machine language, when it processes a line of machine language, it's going to call its internal magic tricks to actually perform the various logic things. All right. So there has to be a mapping that occurs. And we've decided that as humans, we really prefer to operate at this high level thing. We, under distress, will operate at the low level thing. But it's going to take like a homework assignment to convert it to machine language, but not something we would sign up for to do that as a job. Make sense? All right. But that mapping still needs to occur. So one of the things you looked at in the book was how does this mapping actually work? And you looked at the ARM. Where am I at here? Oh, that's right. My slides are in the same dealy thing here. So here is us representing instructions. So notice that we have, what does this add up to? 31 bits? 32 bits. 15, 21, 32 bits. And it's a 32-bit architecture. Well, actually, most of our architectures today are 64 bits, but the instructions in ARM are left. I mean, ARM has been around for a while, back when even 32 bits was the biggest architecture we had. So an instruction size, an instruction field is 32 bits in size. Okay, so now we got to decide, well, how do we split stuff up into that field? So they've given us kind of an example here. So we have the actual instruction itself is represented as 11 bits. So what does that mean about what's the maximum number of instructions we can possibly have in ARM? Not necessarily the actual number of instructions we do have, but what's the total number of instructions we could have in ARM assembly language?
2 to the 11.
2 to the 11th. So 2 to the 11th power is the maximum number of unique magic tricks that we could call upon if the language were to grow to that point. I don't know how many instructions are actually in existence, but it's less than 2 to the 11th. It's definitely less than that. All right, but that shows us kind of maybe where it could grow to. So in any case, they're using the those 11 bits for the actual instruction. All right, so then these next things, so our parameters that are coming in, so whether it's the destination register or the internal register, like this is the destination register, this is the second parameter, this is the first parameter. So these guys are 5-bit addresses which represent a register number, right? Probably a register number. They could also be immediate values, but for right now, let's just say register number. All right. And then this guy here in the middle, this unused 6-bit thing, that's for shifts. Okay. And it's not used in 2.5 here, but they introduce left and right logical shifts in the next section. And that's where that guy comes in. So so in this bit field, it tells us all the information that a CPU would need to actually carry out a magic trick. That is, what's the trick I'm carrying out? That's this part right here. Followed by, where am I sticking the result of carrying out that instruction? Okay. Followed by possibly nothing, but also possibly one of the parameters to the instruction if it requires a number of shifts. Okay. Followed by the parameters 1 or 2 or potentially 0 if there's no instructions to or no parameters to an instruction that are required for making this work, the 2 inputs, up to 2 inputs. That makes sense? So they've decided that we're going to have a data representation language that says we're going to put some of the stuff here, and that means the instruction. We're going to put some stuff here, some stuff here, some stuff here, some stuff there, and all that together gives us all the information. It's representing all the data that we need and actually in order to actually accomplish or to carry out a magic trick. All right, makes some good sense. All right, so now I mentioned earlier, well, not earlier today, but earlier in the course that we were going to write our own ARM interpreter, right? I guess it's roughly an interpreter. I guess we can call it an assembler, but we're going to write it as an interpreter. Okay, so that means we need to have a way of representing an instruction. Okay, we need to create this bit field, and we're going to start looking at that today. One thing I'll kind of throw out there, so we'll talk about this on Tuesday because we do not have class on Thursday. It's fall break, right? So on our midterm exam will be a week from this Thursday. So not the next time we meet, but the time after that. On Tuesday, when we come back, I'll go through the slides and talk about kind of what I think is important, what I don't think is important, blah, 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 so you kind of know what's going to be in the exam. It's the usual exam, 10 questions, 10 points each. There will be some assembly programmy type stuff on there, but probably a significantly higher chance of having to read assembly code. Say, what does this stuff do, or what's the final result of some register, and there will definitely be number conversion stuff on there, and as you might imagine. So, because even in classes that aren't related to number conversion stuff, there's number conversion stuff. So there's definitely going to be number conversion stuff. But it's my usual policy. If you do better on the final exam than you do on the midterm, I'll replace your midterm exam score with the final exam score. So hopefully it's lower stress. So if you come in and bomb it, learn from your mistakes, and then do better on the final, blah, blah, blah. Make sense? All right, so we'll talk about the details of that on Tuesday, but let's kind of get started with our data structures here related to this. So we're going to have to create a data structure for representing an instruction. So didn't I open up Android Studio? Oh, I'm so sad. I thought I did. Let that cook again. All right. Create a new project, and we're going to call this guy ARM Interpreter. And we'll do this for API 15. I'll create an empty activity. It's my starting point. All right, now while that's cooking, I just want to cover one more thing here in the notes that's going to be fairly handy for number conversion stuff as we get in here. I'm just going to call this guy the shortcuts. So we have convenient shortcuts for going, and you saw this in, I don't know, 2.6 or 7 or somewhere in there. Convenient shortcuts for going from binary to octal and binary to hex, from hex to binary, from octal to binary. They probably didn't spend that much time focusing on the octal, but they probably focused quite a bit on the hex, right? So, for example, if I gave you the value FA2 in hexadecimal, and I asked you, what is the binary version of this, what would you say? How do you convert that to binary? Well, old school, we would have gone and done all the, converted the F to a 15, the A to a 10, the 2 to a 2, done the ones place, the 16s place, the 256 place, done all that stuff, and ultimately got it into decimal, then gone from decimal to binary, and big, long, drawn-out thing. But with our shortcut, we can represent each of these guys as a 4-bit value, right? Because 0 to 15 can be represented in 4 bits. So an F is 1111, and A is what?
1010.
So that's a 1, 2, 4 is 8, so that's 1010. So that's an 8 plus a 2. And then what's a 2? 0, 0, 1, 0. So take the little spaces out of here, and that is the binary version of FA2. Make sense? Similarly, if I gave you some random octal number, 127, and I tell you that's an octal, because I would have to tell you that's an octal, because that could just as easily be in base 10, right? So I tell you that's octal. So 127 in octal, that would be, now we do 3-bit values, because the legal bits in octal, well, the legal octets in octal are 0 to 7. So a 1 would be 001. Well, 0 to 7 can be represented in 3 bits, right? 111 is a 7. It's the 1's place, the 2's place, the 4. So 4 plus 2 plus 1 is 7. So a 1 is 001, a 2 is 010, and a 7 is 111. So that is the binary version of that octal value. Make sense? So that kind of explains why octal is just randomly selected as one of the values that's often used in computing, because we have an easy way of mapping to it. All right. Similarly, base 4, which we've referenced as a nibble, that could also be, even though it's not common to represent a number in base 4 because you're almost as bad as binary at that point, but you can work with nibbles in 2-bit chunks. All right, so that's why that half a byte or the nibble is convenient for us. All right, so these are shortcuts that are helpful for us to move between binary and hexadecimal. Now, what about decimal? Do I need a shortcut to move from hexadecimal to decimal? Who uses decimal? We do. Okay. Now we look at our assembly instruction. If we want to add an immediate value, right, we're putting a decimal value in there for the immediate values, right? ARM is doing us a favor. Say, look, we realize you're human. You like decimal. So we're going to let you do immediate values represented in decimal. And then what's the assembler going to do right off the bat? It's going to convert it into hex for it to actually work with the values. Or binary. It'll probably convert it to hex for footprint, and then it can move between hex and binary trivially. So the only reason we even see decimal in there is because we're involved. Does that make sense? So we don't really need a shortcut for converting between hexadecimal and decimal. Okay, so just wanted to throw those shortcuts out there because that might come in handy. Probably not what we're writing today, but will come in handy eventually as we're moving between binary and some other stuff. All right, so going back to this guy right here. So we have our 32-bit space right here. So in that 32-bit space, we have to keep, so really, I mean, when I create an instruction object, okay, an instruction data structure, I'm going to have to hold on to 5 different pieces of information. One of the pieces is going to be an 11-bit value. Another piece will be a 5-bit value, a 6-bit value, a 5-bit value, and a 5-bit value. So how do we represent values of certain bit sizes? So if you're writing a, let's say a Java program, and we want to represent an 11-bit number, 11-bit value, and at the same time we also want to represent a 5-bit value, how do we create containers for holding those values? What's the correct data structure for us to represent bits? Or what's a reasonable data structure for us to represent bits? If I'm storing something like 100111, how can you store something like that in Java?
Variable?
A
variable?
Okay, tell me more. What kind of variable? So definitely, if we're storing anything in Java, it's going to be in a variable. So that could be an int, it could be a char, it could be a boolean. So tell me more about these variables. Just the variable was a guess. Okay, so if I give you something, oh, we want to switch out of this. If I say I want to store this value in Java, what kind of thing are we familiar with that allows us to store something like that? Hey, we could do, well, a string array. Yeah, you could do it that way, but that's kind of an overkill. So maybe a string. Yeah, so I mean, I could just put double quotes on each side of this guy. That guy's a string. No harm, no foul. I could also probably store it inside of a number, an integer array, or probably a byte array would be the most cost-effective or something like that. Since we can't go smaller than a byte array, it'd be nice if we could have a bit array for a footprint, but maybe a byte array allows us to store some number of bits with some number, a certain size associated with it, and then we can give ourselves some helper functions, maybe for getting values in and out of it. Okay, so let's kind of start with that. So before we create an instruction, we need to have a way of holding a value of some number of bits. All right, so we can kind of design it in here. So let's call this guy a binary value. So we're going to create an object called binary value. All right, and this guy is going to have a number of bits that he's going to store. All right, and then we can also store the, maybe it's a byte array of those bits. All right, so we're going to create a data structure for representing binary values, and we're going to have a couple different ways of constructing this, because we might want different ways of constructing this. We might want to create a quick binary value thing that can just hold 11 bits of something and have it autofill it with zeros, for example. We might want to have a way of creating a binary value, passing it a string representation of our binary number, and just have it do the magic behind the scenes. Stuff like that. All right, and then if we need to add some other conveniences to it, we can. So let's write these couple of things. Close this guy, but open this guy. All right, so, hold on a second, my left eye is all blurry. All right, we're back-ish. All right, so I'll create a new Java class, and we're going to call this guy, what did I say, binary number? Is that what I called it?
You called it a binary value.
Binary value. All right, so binary value, we'll hit OK here. Is this text big enough? We see that? All right, so we have our binary value. We're going to store a couple of pieces of information. We've listed those pieces of information. We're going to have a number of bits, and then we're going to have a byte array that's representative of that. So I'm going to create a private int number of bits, and then we'll have a private byte array. We'll call this guy the bits. And then we're going to create a couple of different constructors for this guy. So we'll have a constructor that just takes in a number of bits. We'll set the number of bits. We'll build our array and then fill the array up with zeros. It actually defaults to zeros, but we'll fill it with zeros anyways just to be, I don't like relying on default values. So we'll say public binary value. All right, and this guy is going to take in a number of bits as a parameter. So very first thing we'll do is we'll set this dot number of bits equal to the number of bits that was passed in. All right, then we'll go ahead and give a value to our bit array. So this dot the bits is equal to a new byte array of size this dot. Well, actually, I could just use the number of bits that was passed in. Okay. So there's that guy. And then if I want to use something, so historically we could have just say, so for int I is equal to 0, I is less than this dot the bits dot length, I plus plus, and then I can say this dot the bits at bucket I is equal to 0. So that'll go through and it'll fill it up with a bunch of zeros, even though I promise you it was already filled up with zeros, but we don't want to trust that. If you want to see a Java shortcut to this, there is a class in Java. I'm going to go ahead and show this to you. Well, that's not fun. So inside of java.lang, part of Java that comes with it, we have a class in here. Oh, is arrays not in there? Arrays no longer in lang? Is it at a higher level? That's got to be in java.lang. I'm going to cheat here real quick. Java.util. Interesting. Okay, so inside of java.util, we have the ability to take in a byte array and a byte value and fill it up. Is this a class method or an instance method?
Class method.
Let me resume to where I was. Ninja. It's so hard to zoom on this computer. Oh, there were the F's. There we go. So you said it's a class method? How do you know?
Static.
Static. So this is a class method because it has static in front of it. How do we call class methods? Use the name of the class in which the method was defined. This guy is inside of a class called arrays. So I can say arrays.fill. And I can say I want to fill my array called, what is it called? The bits. And I want to fill it with zeros. Now notice it's screaming that it can't resolve a method. Oh, actually, do I need to say Ooh, how do I say the byte? I just have to cast it? That wasn't as fun as it should have been. All right, so notice it imported java.util.arrays. So I have this function called arrays. Well, I have a class called arrays. I called his function fill, passed it my array, passed it the default value I wanted to fill it with. So that line I have highlighted right there does the same thing as this loop. Make sense? So if you want to have a nice convenient way of filling up an array with stuff, it's built into the language. If you didn't know it was built in the language, just write the little loop and move on with life. All right, so we'll leave our little arrays fill thing in there. So I set the number of bits. I created my actual array. Then I filled it up. Now we might have a second version of this constructor. And this guy might take in a string bin as a parameter. Now, what's it called when we have more than one method or constructor with the same name but a different number and or type of parameters? Polymorphism. All right, so we have a second constructor here, still called binary value, but this guy takes in a string as a parameter rather than an int. So this dot number of, oop, I lost my curly braces. This dot number of bits, how many bits does this particular binary number have in it? Who?
Bin.length.
Bin.length. Bin.length number of bits. All right, so then we're going to say this dot the bits is equal to a new byte array of length this dot number of bits, or we can say bin.length, whatever makes you happy. Something along those lines. If you want to get be like super object oriented about this, like super object oriented about this, you could do this. You could say private binary value, and this guy would take in a I was going to create a separate constructor that just builds the size, but I already have a guy here that takes in a number of bits. So with that in mind, one thing I could do here is rather than create my array of bits here, I can go ahead and I can say this bin.length. That has to be the very first line. So pretty uncommon actually to see this. You've seen when we call our parents constructor before, when we deal with inheritance, you say super. A constructor can actually call another constructor inside the same class using the this keyword. So, but it has to be the very first thing that happens inside the constructor. So inside of binary value, the very first thing I'm going to do is I'm going to call upon one of my other constructors. So I do this by referring to myself. I'm passing in the length, which is an int. It's going to call this version of the constructor. It's going to set the number of bits for me. It's going to then create my bits array, and it's going to fill it up with a whole bunch of zeros. Then I can differentiate myself here by going through and filling up that array with the binary, the bits from bin. Does that make sense? So now I can go through here and I can say for int I is equal to 0, I is less than this dot number of bits, or I could say this dot the bits dot length I plus plus, or I could have said bin dot length. All those things are synonyms, right? So after I call the constructor here that sets number of bits to whatever number I passed in, at that point in time, bin dot length is the same value as the bits dot length is the same value as number of bits. Those all hold the same number. So I'm going to spin through every element of my string. So if it makes you feel better, you can refer to the string here as bin dot length, but it's going to be the exact same number as we had before. So I'm going to go through every element of the string, copying the value from that over to our array. So what I'll do here is I'll say this dot the bits at position I is going to equal some value. What value is it going to equal? Well, I'm looking at, in my string, I'm either going to be looking at a 0 or I'm going to be looking at a 1, right? And that's going to be the char 0 or the char 1. So I could say bin dot char at I equal a 0. If I'm looking at a 0, then boil down to a 0, otherwise boil down to a 1. And these are the byte versions of 0 and 1. All right, so another fun use of a inline if statement. So I'm calling upon my other constructor to go ahead and do the work of setting number of bits, creating my array, filling it with a bunch of zeros. Then I'm going to go through here and loop through my string, copying into the bits either a 0 or a 1, depending on the character currently represented in the string. Make sense? All right, so now I have a binary value representation where a binary value has a number of bits and then it has an array that actually holds the bits as zeros and ones in terms of bytes. So 10 bits is actually equal to 80 bytes. Well, it's actually equal to 10 bits, but it's 80 bits rather. Yeah. So it's very fat bits is what it comes down to. All right, so that's our binary value. Go back to our guy in here. So now we have the ability to represent a binary value. Now we need to give ourselves a data structure. We might add the binary value as we need it, but we're going to give ourselves a data structure for representing an instruction. All right, so we're going to create a, if we want to be specific here, we're going to call this an ARM instruction. All right, and our ARM instruction is going to have several different parts here. So if we stay here, go back into here, we have the instruction itself, followed by our destination, followed by our shifts, followed by our, what is this called, source 2 and source 1. I don't remember what they actually call those guys. Did they label them somewhere in here? Well, I'll just name them myself. So instruction, destination, shifts, so we have instruction, and this guy is 11 bits. We have destination, this guy is 5 bits. We have shifts, that's 6 bits. Then we have source 2, that's 5 bits. Source 1, That's 5 bits. Right? So those are our things for our instruction. So what we want to be able to do is we want to be able to go through our instruction and have all these things. We want to be able to create an instance of an instruction and have it create these various parts of our instruction. Now, our instruction might come in several different versions. We can create a generic instruction that just builds out our bit spaces so that's kind of ready to put stuff into it. Now, we might also want to have an instruction that actually takes in a string representation of an ARM instruction and does the stuff that we were doing from our in the book, right? I think the book probably gives us a list of kind of the instructions we have now and then the 11-bit value somewhere in there. If not, we can maybe make that up, but whatever, we'll have our instruction thing. So we're going to look at a couple of constructors for this. Now, the real reason we're doing it, the real reason we're going through this exercise is up until this point, very rarely have you taken a real problem and translated it into a software application, actually doing that mapping. So now we're saying, okay, well, we're learning about instructions and binary spaces, binary values, whatever. How can I represent these real life things as objects if I'm building a larger application? Okay, as opposed to in a class, you might get a starting point and then have to go from there or something like that. So this is allowing us to really think about things you might do when you're writing software in industry. All right, so we're going to go ahead and create our ArmInstruction object. So we'll right click here, new Java class, ArmInstruction. Did I spell that right? Yeah, close enough. So ArmInstruction, and this guy is going to have 5 different fields. So we have private, binary value, then we have instruction, and we have private, binary value. And actually, since these are all binary values, we could put them all on one line if we really wanted to. So we have a binary value instruction, we have a binary value destination, then we have shifts, then we have what I call it source 2 and source 1, something like that. All right, so those are our fields. We have 5 fields. Then we'll have a constructor, so public ArmInstruction. This guy will take in, actually we're going to have him take in nothing and go ahead and initialize our fields to the correct sizes, because an ArmInstruction knows that the instruction field is 11 bits and the destination is 5 bits. It knows all these things, right? It doesn't require given information to solve that. So we'll say this dot instruction is equal to a new binary value. And in this case, we're going to use our constructor from binary value that just takes in a number of bits. So we're going to say that an instruction size is 11 bits. Similarly, we'll say this dot destination is equal to a new binary value, and a destination is going to be 5 bits. This dot shifts is equal to a new binary value, and this guy is going to have 6 bits. This dot source 2, well, you can do it in whatever order, but is a new binary value of size 5 bits. And this dot source 1 is a new binary value of size 5 bits. All right, so you see how we're using that data structure we created? Now, why do I keep calling it data structures? When you took 300 and we talk about data structures in there, or for those of you who've had 300 already, what are our common data structures we've discussed? Stacks, queues, linked lists. What would you say? Heap. Oh, we do talk about heaps in there. It depends on time. Sometimes I don't talk about heap. We did it in your class. Yeah, so heap is a priority queue, right? So then trees, binary trees, AVL trees, stuff like these are traditional data structures. But what is a data structure?
Something that holds data.
It's a structure for holding data, right? Okay, so it's some sort of organized way of holding data. Isn't that what an ARM instruction is? Are we holding some structured data here? Sure. Fine, it's not one of our traditional data structures. It might not be a data structure that a lot of people might ever use in their life, but hey, it's one that fits the purpose that we need for right now. So now we don't have to remember that the instruction is 11 bits or the destination is 5 bits, so on and so forth. This guy knows it for us. Okay, similarly, we might want to have a ARM instruction let's see, what can we do with this? We might want to have an ARM instruction that takes that can be built with a couple of different parameters. So I'm just trying to think ahead on this. So some of our instructions have, well, all instructions have an instruction name, right? Some of our instructions have a destination and a single source. Some have a destination and 2 sources. So what we can do is we can actually have different versions of the constructor that allow us to pass in the pieces and then build out our instruction based on that, or build out our ARM instruction based on that. So I'm going to say we have a string coming in called instruction. And so let's just use kind of our default ones. I think the book starts with like adds and subtracts that have an instruction, a destination, nothing for the shifts, and then the 2 sources. All right, so let's kind of operate off of that guy. So we have string instruction, then we're going to need a destination, then we have a string source 1 and a string source 2. I'm actually going to list these. Do I want to list these backwards? Because it's like, if we do, it's add x1, comma, x2, comma, x3. That adds x2 and x3 together, storing the result in x1. But when we build out our instruction, it's the x1 is the destination, but the x3 is source 2 because it actually flip-flops those. So do we want these flip-flopped here, or should we leave them in the right order here and just let the flip-flopping happen internally? We could just...
Flip-flopping happen internally, so it's less you have to think about.
Yeah, makes sense. All right, so ARM instruction. So one version of an ARM instruction, we could pass it the string representation of the instruction, the string representation of the destination, the string representation of the source, and, well, the 2 sources. Now, sources can come in a couple of different flavors, right? Okay. One flavor is a register. Another flavor is a what? What's an alternative to a register as a possible source?
Pointed to it.
That's actually true. So what's even another alternative? An immediate value? Yeah, so I could actually put an immediate value in there. All right, so let's call this guy, I'm going to call him source reg 1. I'm going to call this guy source reg 2. So we'll make this guy specifically built for registers, because I think we'll have to deal with memory addresses offsets differently, and we'll have to deal with immediates differently. All right, so we'll just keep this straightforward to begin with. All right, so now I'm going to need to do some lookups. I need to go and look up this instruction to find out what the 11-bit value is for that instruction. All right, so we're going to create another class. So let's call this guy ARM want to call it like arm mapping, but do I use the M for both, like arm map? Haha, get it? Arm map. I like that. So we're gonna go with arm map. All right. So what's this guy gonna do? It's gonna do several different things. It's going to take a string representation of an instruction and return the 11-bit binary value for that guy. Another thing it's going to do is it's going to take a string representation of a register and return the 5-bit binary value for that register. All right. And we'll probably do some stuff with immediates and memory stuff too. But right now, these are the two things it needs to do. Now, I know earlier I said there was probably a mapping. Did I lie? Is there a mapping in here? Did it give us like a list of like add, subtract, and what the instructions are? I know they, they basically say, oh, by the way, add is this guy. Here's your 11 bits for add. But does it actually give us a chart somewhere in here? Let's see. Otherwise, we can just look it up. I'm sure there's a no, not it. It's conversion stuff.
I don't think it had the actual binary.
Well, it looks like we have add, subtract, add I, subtract I, and then so we almost have the binary values, right?
Yeah.
So if we start off by just having adds and subtracts and add I's and sub I's, and yeah, we can run with this, can't we? Yeah. We'll expand our instruction set as we move through here. So we'll start off with a very small instruction set because that's all we're testing against anyways. All right, so I'm going to create another class, RMap. I love that name. That's so fun. Am I too easily entertained?
You missed us too.
Huh?
You missed us too.
Did I?
That was nice.
Although, couldn't you say that really the stuff that's happening right now could happen without an audience? I could just be sitting here because I do this. My wife asked me why I'm babbling to myself at the house. Sometimes I have full-blown conversations with Mr. Gonzalez. Not even kidding. It's so funny. All right, so we'll have our AR map, and what we want to have is we want to have a collection of mappings between instruction names and the equivalent binary values. And actually what we'll do is we'll give our binary mapping thing a power up, because I think where's our binary value? We have a string bin. Oh, I don't like that. Nah, whatever. We won't give it a power up. We're going to leave it alone. All right, so what I'm going to do is I'm going to create, maybe do this as parallel arrays. No, what kind of fun is that? So we have an AR map. Yeah, I think we should do it that way. Otherwise, we'll just have all these extra classes laying around. Yeah. So I'm going to create a private private static string array called instructions. And this guy will have add. We'll just do add and subtract initially, since we're only supporting those type values right now. We're not doing immediate ones yet. So we'll just have 2 instructions that we know about. Then we'll have a private static int array instruction mappings. And this guy is going to have the add and subtract mappings. So add is 1112. And subtract is 1624. Let me just make sure that these are the values that we're using the right things here. Where's my number? Well, that's a crappy calculator. All right, so 11,000 is the last thing. Yep. So that's the right mapping. So they've given us the opcode for this is the decimal value. We're going to have to convert it to the binary equivalent, and we have a Java thing that'll do that for us. But we need to make sure it's 11 bits. Well, then we should write our own. All right, so what was I doing? Oh, yeah. So we'll say private string decimal to 11-bit binary. This guy will take an int opcode as a parameter. And we're going to go ahead and we're going to create a string and fill that guy up with it. So we'll have a string answer is equal to the empty string. And we'll say while opcode is greater than 0. We'll say answer is equal to opcode mod 2 concatenated with answer. And then we'll say opcode divide equals 2. So we'll build it in reverse. Right? We just keep dividing by 2 over and over again, recording the remainders as soon as opcode is equal to 0. So if you want to say greater than or equal to, if you want to say not equal to 0 here, that's fine too. But as long as it's greater than 0, we keep going. So when opcode finally gets to 0, we will have already had our last thing. So this guy should now be built correctly. Now I need to ask the question. So I'm going to say for int I is equal to, we'll start off with answer.length. Keep going as long as I is less than 11, I++, and we'll say answer is equal to 0 concatenated with answer. Then return answer. So this will build a binary string. Then this will go ahead and pad it with extra zeros up front to make sure it's always 11 bits big. And then we'll return the answer. Okay. There's probably a built-in string padding function in Java too, but whatever. All right, so let's say this guy's good. We'll test it actually here in a second. So 1112. This is AR map. Let's come in here. I'll just put it in on create. AR map. Oh, I need to make that guy public for a moment. Oh, did I not make the method static? Oh, I didn't. That's what. Now he's happy. So we'll just test it real quick. We'll pass in the 1112 thing into it and see if we get the 11-bit binary equivalent for that add instruction, just to make sure our little map function there is working. And this should end up down here in the, well, it'll pop up in the console, or logcat, right? Isn't that what it's called? Logcat. Yep, here's our value. 1, 2, 3, 4, 5, 6, 9, 10, 11. All right, so that seems to work. We've tested it exhaustively on all values. so it's got to work, right? All right, so that's our AR map, dealy flippy thingy majiggy. So we have two instructions here, add and subtract with the binary or the decimal equivalents. I'm going to switch this guy back to private. And then what we're going to do is we're going to give ourselves a public method that will take in a value like this. So take in an instruction, and why don't we convert the instruction to uppercase? That way we guarantee it's always, whatever they pass us, we can handle. Then we'll get the same value from the instruction mapping, and then ultimately spit out a brand new binary value for that. All right, so we're going to say public static. This guy is going to return a binary value. And we're going to say look up instruction. We'll take in an instruction as a parameter. and we're going to search through instructions for this instruction that was here. And for right now, we can just assume that any instruction they pass us is actually there. We don't have to do any error checking for it. So we're going to search through here. So for a second here, I'm going to say instruction is equal to instruction.to uppercase. So we'll just, whatever they give us, we'll just make sure it's in uppercase. Now we're going to search through instructions. So for int I is equal to 0, I is less than instructions.length, I plus plus. If instructions at bucket I dot equals instruction, if I'm looking at the guy that we care about, then I'm going to get my binary string. This guy returns a string. So I'm going to return a new binary value built from a binary string. What string? Decimal to 11-bit binary of instruction mappings of bucket I. So this is the opcode for the instruction that maps to the instruction we just found. This will boil down to the 11-bit binary equivalent of that opcode. Then as a string, I remember from binary value, we have a version that takes a string in as a parameter. So I'm then going to build a binary value out of that and ultimately return that. Now, this guy's not happy right now because I've advertised I'm returning a binary value, yet I only situationally return a binary value here. So what I'll do is just my backup plan. I'll return a null down here, even though I've said that will never happen. So we'll just put we assume every mapping is found. So this should never get hit. Bad programming practice. So don't do that, but we did it. Save time. All right. So that's what this guy does. When we say lookup instruction, it's going to ultimately give us a binary value version of our instruction. And then binary value looks like this. And then what I'll go ahead and do is I'll give us the ability to print out that array. So let's just say public string to string. Let's just say public void display. So we only focus on one thing at a time. We'll say string answer is equal to the empty string. For int I is equal to 0, I is less than this dot the bits dot length, I plus plus. And we'll say answer plus equals this dot the bits at bucket I. And then we'll say system.out.println answer. So we've taught our binary value how to display itself. And then lastly, what we'll do is just to test this on that backside, we're going to look up add using AR. So AR map, we're going to say we want to look up instruction. We'll pass it add as a string. It's then going to go through here, find add, get the opcode for it, convert it to a decimal to 11-bit binary, build a binary value out of it. Then we'll ask that binary value to go ahead and display itself. And we should get that same binary number we just saw. Okay, proving that we zigged and zagged through all the hoops. Okay, so we're going to do AR map dot lookup instruction add. That's going to give us a binary number that will tell to display itself. Oh, I can't print that out. I got to do this. Display does all the printing. So I don't need to say system.out.println. All right. right, so we'll look up the add instruction, which ultimately this guy will produce for us a binary value. Then we'll ask that binary value to display itself. Run this guy, and we should get the same binary value as we've been getting. I think that's it. Let me just run it again to make sure that's the thing that printed. Yep. So looks correct. So all of our pipes are seemingly hooked up, and we're able to do a lookup on ARMap for those things. Now, secondarily, what we want to be able to do is we want to take in our register names, right? And our register names are, isn't it like X and stuff? What's the register names in this thing? So X1 through X31? All right, and then the 5-bit mapping to that is the 5-bit decimal equivalent of the 1 or the 2 or the 3 or the 4, right? So what we would do is we would, oh, I'm lost. So inside of ARMap, we're also going to have mappings for our, so we have private, static, string array, call this guy registers, and this will be what I'm actually, whatever. So this is X1, comma, X2, so X3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, X1 through X, well, there's an X0 too, isn't there?
Mm-hmm.
That. All right, so we have all that, and then what I'll do is we need to finish updating that, so I'll get rid of the P there in front of that. So that's a little error message, and then we'll say finish mapping here for mapping from our registers to our 5-bit numerics for our registers. All right, questions about any of that? I'll go ahead and I'll share this on, yeah, a lot of questions. I'll go ahead and share this on, what am I doing? How do I, oh, is this it? Import into version control, share project on GitHub. So you said there are lots of questions on this? Oh, or she made a joke or something?
I made a joke.
Oh, was it a funny joke?
Well, she thought it was funny because it had to do with her.
Oh, I see. All right, so. All right, so the code's up there on GitHub. I'll just give you a link to it. No homework over break. I'll see everybody on Tuesday. We'll talk about the final. Sound good? Ooh, what? Yeah, midterm and the final, and next week.
Why?